just instantly lights. That's the first time I've ever done that. So cover, and it's out. Isn't that cool? Flynn Dog Science with me, Caleb Flynn. Subscribe, like, comment, and hit that bell. Hey fellow science lovers, today we're going to be doing the coolest hot reaction, combustion. And as we do combustion, we'll be doing a whole bunch of experiments to demonstrate two main principles. We're going to look at conservation of mass, which just means we'll learn about this term reactants and products. Or I guess maybe reactants and products. And those reactants and products, we need to say what happened to the atoms that we started with that lit on fire, and how did those become the atoms and molecules that we saw later on. And then the other thing we're going to check out is where did the energy come from to make the fire? It had to come from somewhere. So we'll learn about that. Let's go ahead and get started. We'll do a whole bunch of experiments now. First experiment, I got 70% isopropyl alcohol and I filled up this little beaker. Let's watch and see what happens when I try to light it, and then what happens when it's lighting. Here we go. Look, it didn't light. Let's keep going. I'm putting the fire on and it's like it doesn't want to light. Isn't that weird? You'd think it'd just like light instantly, but it's not. There it goes. It's starting. Can you see that there? Got the flame right at the top. Oh, it's so cool. Hot, so hot, so neat. Let's make some observations now as we check this out. So what do we need for fire to occur? The first thing that I want us to notice is, hopefully something that you notice, is that we're burning something. We have a fuel, and our fuel right now is this isopropyl alcohol. So we have this isopropyl alcohol burning here. The second thing I want us to notice is where the flame is and where it is not. The flame is at the top, above the level of the liquid. So the flame is not down in the liquid. And why is that? This is one cool thing about fire that we'll learn, is that fire requires a certain percentage of a gas that we're going to figure out in order to light. But that gas, even though there might be some gas down in the liquid, some air, there's not enough of it in order for our flame to actually light. So there's only the right amount of gas mixture at the top. And that's kind of telling us about our other principle, vapor pressure. So vapor pressure we'll look at and see, how does vapor pressure connect here? So we'll look at that just a little bit more in our notes here and how that affects our flame and our flame burning. Okay, let's look at our next piece. We let it burn for a little bit, and so the temperature of our liquid increases. So watch what happens when I try to light it now. Remember what happened when I tried to light it last time? Okay, let's watch now. Instantly, didn't even have to get close, and all of a sudden it's going. Let me see if that, you can see it a little better there. My hand is a backdrop, I'm not sure. So all I had to do was get it close. Watch again. Just instantly lights. Isn't that so neat? So the temperature here, and that's what we'll look at in terms of vapor pressure. Why is it so much easier to light when the temperature gets warm? Let's think about other things that are required for this to burn. So if I light our alcohol, okay, we let it get going. And we know, okay, we need a fuel in order for this to burn. What else do we need for it to burn? Well, let's go like this. If I take this little watch glass right here and I set it on top, it almost instantly goes out. Watch again. Okay, lights, it's going. Set a watch glass on, almost instantly goes out. So now you might in your mind go, okay, I know what it is. I know what goes into it, which is cool. That's great. I'm glad you do. But let's test and see. So what I did is I did a little secondary experiment, okay? I don't want to distract us. I love getting on bunny trails. This is just oxygen gas I put in this balloon, okay? So little oxygen gas, I put a little valve on it and then a little hose so I can be a little further away. And so what I'm gonna do is, in my mind, I'm saying, okay, I think it maybe is oxygen that is needed in order for this flame to burn. So if I light this, okay, I'm saying oxygen gas is coming in from the air. And when I put this on, I cut off the oxygen gas and so it goes out. So if oxygen gas is helping this burn, what would happen if I put more oxygen gas on it? So what I'm gonna do is I'm gonna use my little balloon here, and it's a little bit of pressure in here, and I'm gonna blow some oxygen gas on this. So if oxygen gas is needed for it to burn, my thought would be is that our flame would get, what do you think? Let's try it and see. Now I'm gonna get a little ways away. Oh, that was so cool. That's the first time I've ever done that. Oh, that was awesome. So oxygen gas, when we put that oxygen gas on, the flame got a lot bigger. And just to make sure it's not just air, here, watch when I blow on it. Okay, it gets a little bigger, but more spreads out. When we put the oxygen on, that flame got bigger. And now we can see we probably heated up the alcohol a little bit, and so that changed the amount of combustion that we have going on too. So the two things we know about so far, we need a fuel source, the alcohol, and we need oxygen gas in order for a flame to burn. That was so cool with the oxygen. Never done that. Now, let's start thinking about what's coming out of the flame. I'm gonna get this big beaker here. Okay, I'm gonna light this on fire, and I want you to notice the beaker. Watch what happens to the inside of the beaker. So this alcohol is a little cool again. We'll let it get warmed up. Watch what happens to the inside of the beaker walls. Can you see this? They're getting all foggy. Isn't that so cool? So the inside gets all foggy. So in your head, you might be like, I have some ideas. Maybe you think it's alcohol that's on there, because that's what we're burning is alcohol. So let's look and see. If it was alcohol, watch what should happen, right? You would think alcohol would light on fire. So if I light this, those walls are not lighting on fire, and if I rub them, they're wet. The walls are wet. So what's actually coming out of fire, which is cool and definitely surprising, is water. Water is coming out of fire. So one of our products from combustion is H2O, water. So let's look at another cool principle. We light the alcohol. Watch how long the alcohol burns once we cover it with the beaker. So we'll see the walls start to fog. Oh, we see that water forming, but it's still burning in there. It's still burning. And then, okay, it just went out. I think, is it still flickering? I might have saw just a little flicker. Okay, now watch this. I'm gonna relight it. Now think about how long it just burned. It's out. Okay, watch that again. I relight it. Something is being produced by our flame that is putting the flame out prematurely. So if we do this again, right? This is our beaker and we're lifting it up so air could get in. Cover it. It's out. So what is being produced there? And this is where conservation of mass really comes in very handy, where we can think about, okay, what is the makeup of H2O? It's hydrogen and oxygen. And what must this other gas have in it, this colorless gas? Well, alcohol had carbon and oxygen and hydrogen. Oxygen, gas just had oxygen, which means there must be some gas coming out that has carbon in it. And so our guess might be one of the really common gases is carbon dioxide, which turns out is non-flammable. We can imagine that this has a lot of carbon dioxide now inside of it. So cover, and it's out. Isn't that cool? So this colorless gas that's being produced actually puts out the flame in addition to running out of oxygen inside. So we'll continue to think about those two thoughts in balance here. Look at this little staircase of isopropyl alcohol we have now. We have 3 different levels, and what I'm gonna do is light them and cover them, and let's see which ones go out first. Thinking about that oxygen is needed for the flame to burn, and CO2 is getting produced by the flame, and if you calculated which one is heavier, the CO2 is heavier, so it should sink. The oxygen should be at the top and the CO2 should be at the bottom if everything was the same. So let's do this experiment. We'll light them all. All 3 are now burning. Remember, CO2 gas is heavier than oxygen, so it should sink. Oxygen is lighter than CO2, so it should be at the top. Let's check this out and see. Top one's out, middle one's out, bottom one's still going. It's out. Think about what that means. Let's do it again. We'll get some fresh air in our beaker. Light the top, lights easy now. Middle, it lights easy now. What's going on in terms of vapor pressure, do you think? Light the bottom, it lights easy. Okay, you ready? Now watch again. Who's gonna go out first? And again, we saw this one go out, then that one, and then the last one, which is weird because the oxygen should be at the top because it's lighter, and the CO2 should be at the bottom because it's heavier. But we'll have to figure out our results when we get to our notes. Out, middle one's out, bottom one's still going. Same result. And it, thought it was out and it came back. Isn't that really cool? So it's showing us something is going on. So either there's not enough oxygen at the top or there's too much carbon dioxide at the top. There's not enough oxygen in the middle, and then there's too much CO2 in the middle, and then eventually there's not enough oxygen or too much CO2 at the bottom, and it goes out. One last thing we can kind of do to check this out. Okay, now watch my lighter. It's out. So the lighter goes out. Try it again. It made it higher that time. So now, at first it went out about halfway, and then later on, it lit. And it goes in. So CO2 is leaving this flame and it's going somewhere. So I put the lighter in. Put the lighter in. And it goes out. Okay, let me try to light it at the top. It will not light. Cover our flame. And we'll think, where is the CO2 gas going? And then it goes out. So that's really kind of cool and surprising because the CO2 gas is hanging out here at the top, at least at first. And that's a really fun, trippy thing, that it's not going to the bottom. And so we'll have to figure out, why is that going on? Why is the heavier gas hanging out at the top instead of sinking to the bottom? Let me show you one last cool experiment, just because we should. It's just a fun one. Showing how the fire follows that airflow. So I put a little isopropyl alcohol on the bottom. Let me put on my glove and light it. Isn't that awesome? That's a flame tornado right there. All you need is some sharks in there and you got a flaming sharknado. That was cool. It's explanation time now. To see the second half of this video, go ahead and check out the link in the description and you can see the notes that we create explaining combustion. I hope you enjoyed doing combustion with me, and I hope you got our takeaways that you need two things in order to do combustion. You need a fuel source and oxygen, and then you produce three things, well, two things with atoms. You produce your carbon dioxide gas, you produce your H2O water, and then that energy is released. And then I also hope you got our main takeaways that the atoms in your reactants rearrange into your products, that the carbon, hydrogen, and oxygen rearrange from the alcohol and oxygen into CO2 gas and H2O water. So the same atoms become new molecules. And then also I hope you get that the energy didn't magically appear, that we got the energy from those bonds being broken and reforming in the reactants and products. Hey, if you like that, subscribe and I'll see you next time. Flynn Dog Science with me, Caleb Flynn. Subscribe, like, comment, and hit that bell.